Okay, these next two examples are a little more complicated. You can see this first one, we're going to say we want to find the area inside r equals 3 sine theta and outside r equals 2 minus sine theta. So of course the first part is for us to graph these two shapes and take a look at them. So we'll do that first. R equals 3 sine theta. We know that's going to be a circle with a diameter of 3. We're going to have that circle is going to be above the x-axis, and because we're dealing with the sine of theta there, we're going to have y-axis symmetry. So we're going to have a circle, looks about like that. So there's our r equals 3 sine theta. And now the second shape, r equals 2 minus sine theta, we have a limacon. It's going to have one flattened loop, since the absolute value of this coefficient is 1 and the a value is 2. We're going to have y-axis symmetry, and because we're subtracting the sine, the majority of our shape is going to be below the x-axis. So we have our kind of anchor points here, and then our shape is going to look something like this. Alright, so we want to know the area that is inside the circle but outside the limacon. So we're going to find this area right here, that shaded region. All right. So some of our landmarks we want to think about. We want to know where do the two shapes intersect? And what I'm actually going to do is I'm going to find just the right side here. So I'm going to find that area, and then I can double it to find the entire area that's actually inside the circle but outside the limacon. Alright, so I'm going to use those two landmarks, and I have to find first what this angular measurement is. What is this angular measurement right here? I know this is theta equals pi over 2. I have to find out what this angular measurement, where these two shapes intersect. So to do that, I'm going to set them equal to each other. So I have 3 sine theta equals 2 minus sine theta. So I get 4 sine theta equals 2. So I'm looking for when the sine of theta is equal to a half. And we know that occurs when theta is equal to pi over 6, when the sine of pi over 6 is equal to 1/2. So here I have theta equals pi over 6. So in order to find I'm really looking for the region that is inside the circle but not inside the limacon. So I can think about that as if I found the area inside the circle from pi over 6 to pi over 2, it would give me all of this area, everything including this, and then I would subtract out the area that is inside the limacon. Right? So I can do that in one step if I kind of do an integration from the outer, I'm going to do the standard area, the outer radius squared minus the inner radius squared. Right, and in this case, the outer radius is, of course, the circle. The inner radius is the limacon. So I can kind of fill in what I know there. I'm going to integrate from pi over 6 to pi over 2. Whoop. Actually, I have to make it pi over 2 if this is going to work. So from pi over 6 to pi over 2, and I'm going to integrate my my integrand itself is going to be, the outer shape is the circle, so 3 sine theta squared minus the limacon is 2 minus sine theta that quantity squared, d theta. All right, so this is, again, the right side of the region that is inside the circle but outside the limassol. And so in order for me to find the entire area that fits what I was asked to find here, I'm going to have to multiply that by 2. So that's my area as a whole there. And once I work through this integral, I should get an area of 3 root 3 as my total area.